Hey everyone, and welcome. Today we're going to jump right in and pull back the curtain on one of the most powerful and honestly important programming languages out there, C++. This is the stuff that powers massive video games, complex financial systems, you name it. But it all starts with a pretty simple question. I mean, just think about it for a second. We are surrounded by these incredibly powerful machines, but they don't speak English, they don't just know what we want. So how in the world do we bridge that gap? How do we give them instructions they can actually follow? Yeah, from the car that gets you around, to the phone that's probably in your hand right now, the laptop you're working on, your game console, even your TV and your camera, they all have a computer inside. And every single one of them is running on a set of instructions. And those instructions? Well, that's what we call a program. It's not a suggestion or a hint. It's a super precise step-by-step recipe that tells the computer exactly what calculations to perform to get a job done. No room for confusion. So to write that recipe, we need a special language, a specific notation that both we humans and the computer can agree on. And that, right there, is a programming language. The one we're digging into today is C++. You know, C++ has a pretty cool origin story. It actually grew out of an older language from the 70s called C, which was famous for being really, really fast. Then, in the 1980s, this brilliant computer scientist named Bjarne Stroustrup, he wanted to add new features to C to handle much bigger, more complicated software. The result? C++. It kept all the speed of C, but added these powerful new ways to organize code, making it perfect for building huge, sophisticated applications. Okay, that's enough theory. The absolute best way to understand programming is to see it in action. So let's write a quick program and make the computer do something simple, something we can actually watch happen right on the screen. Now you might be wondering, why are we starting with a drawing? Well, as Professor Renad says, you master picture drawing, you master programming. It sounds fun, and it is, but it's also a really profound idea. Drawing forces us to think in terms of simple, repeatable steps, and that, my friends, is the very heart and soul of programming. And here it is. I know, this might look a little strange, maybe like a foreign language, but don't worry about understanding every single symbol just yet. The important part is that these few lines of text are a complete C++ program. This is all the computer needs to draw a shape. And check it out. This is what our code creates. As you can see, the computer followed our instructions perfectly. We told a little on-screen turtle to move forward, then turn. It did that little sequence 4 times, and bam, a perfect square. You can literally see our logic in action. So that's pretty cool, right? But how did those few lines of code actually translate into that drawing? Let's zoom in on the key commands and see exactly what we told the computer to do. First up, we've got forward 100. This one is pretty straightforward. It just tells our turtle, hey, move forward 100 little steps and draw a line as you go. And that's how we get the sides of our square. Simple enough. Next is right 90. This command tells the turtle to just pivot in place. It doesn't move forward at all, it just turns 90 degrees to its right. This is how we create those perfect, sharp corners. And here is where the magic really happens. The repeat for command. We could have written forward and right 4 separate times, but that's inefficient, right? Instead, we spot the pattern, draw a side, then turn right, and we just tell the computer to repeat that pattern 4 times. This is called a loop, and it is a fundamental, super powerful concept in all of programming. So here's the crucial point, the big idea. Just like a drawing of a square has a clear pattern, 4 equal sides, 4 right angles, most problems we want to solve with a computer also have patterns hiding inside them. The art of programming is all about finding those patterns, and then using things like that repeat loop to express them efficiently in your code. And that same logic scales up from drawing little shapes to solving incredibly complex problems. Repeating draw a line isn't so different from telling a computer to repeat a calculation on millions of pieces of data. Following the pattern of a square uses the exact same core skill as teaching a computer to find patterns in an image to identify a face. It's the same kind of thinking, just on a much, much bigger scale. And this is why this all matters. Those fundamental concepts, defining precise steps, repeating patterns, that's what allows us to build the systems that book our plane tickets, predict the weather, search the entire internet in seconds, and even simulate the laws of physics. It all comes back to the same kind of logic we just used to draw a simple square. So we've just scratched the surface, but you've now seen the core idea in action. you've witnessed for yourself how a few logical instructions can bring a shape to life on a screen. And that leaves us with a final thought. If a simple loop can draw a square, what could you build with more complex patterns? A few lines made a shape. What could you create with 1,000? The possibilities are truly endless.